All right, so we've spent a bunch of time here talking about different methods of taking derivatives, and hopefully at this point you are starting to get comfortable with the actual process. So what I'd like to do is I'd just like to spend a little bit of time talking about how these derivatives show up in a lot of different contexts in the real world. Because it turns out derivatives are everywhere, and they are useful in all kinds of different fields of study. In fact, what we're going to look at here is just going to be a tiny sliver of all the different ways that derivatives can become useful. So I want to emphasize, this is like just scratching the surface, barely even scratching the surface of where derivatives become useful. Because they will show up in places you would never expect. It turns out, for example, that they're extremely useful in certain types of statistical analyses in ways that you wouldn't anticipate, because you get stuff called the, oh crap, what is it called now? I'm slipping my mind. Moment generating function or something like this. And it involves derivatives and stuff. And so, yeah, but that is a more indirect application. We're going to focus on some very direct applications of this stuff. So one of the most maybe early examples of this was in physics. If we have position given as a function of time, x of t, where x is my position and t is my time, then the velocity v as a function of time is actually equal to the derivative of position with respect to time. And the acceleration a of t, well, that's going to be the derivative of velocity with respect to time, which is actually the second derivative with respect to time of my position function. So this is rather interesting here. What it tells me is that there is this nice relationship, and in a lot of ways, this is kind of what got Newton interested in this stuff. I mean, he was interested in the geometry aspects of it too. But remember, Newton is best known for his contributions to physics. And his contributions to physics, well, essentially, in order to make those contributions, he needed to understand things about positions and velocities and accelerations. Now, he was, I don't believe, the first person to realize that these relationships existed, but this is why he wanted to make precise the ideas of derivatives and things like that. And you'll remember that Newton's third law states that the force on an object is equal to the mass times the acceleration on an object. So to talk about that, you've really got to be able to talk about what is the acceleration of your object. So it is very important. Now, we can take a look at some examples of this sort of thing. So let's say that we want to know a falling object on a planet is following h of t is equal to, let's say, negative 5t squared plus 30t plus 120 in meters, where t is given in seconds. So my height is in meters and my positions are, or my times are given in seconds. Sorry, not positions. Height is my position in this case. We want to know what is the velocity after, let's say, 4 seconds, and also what is the acceleration? Well, this is actually fairly straightforward to answer at this point. Now, it wouldn't be a straightforward question to answer if we hadn't done all the work that we've done up to this point. And this is where I want you to see how far we have come with what we've derived here, we can answer this question, and it's going to turn out to be almost anticlimactic in the sense that what we do is not going to seem that difficult, I hope, to you at this point. If you've been practicing and following everything, hopefully our answer to this question will be fairly straightforward. But before we develop the methods of calculus, this question would be pretty much impossible to do. There would be no way of going about doing this without calculus methods. With calculus, this becomes almost, it's not really trivial, but it becomes a fairly straightforward problem to do. There's not a lot of complication. Why? Well, because the velocity as a function of time is going to be the derivative of the position. What is that? Well, we know how to find derivatives of positions. This is going to be negative 10t plus 30. This is just a polynomial. I take the derivative. This is like the very first thing we learned how to do when we started working out rules for derivatives. So after 4 seconds, v of 4, okay, that's a t, not a 4. Let's put a 4 in there. This is going to be negative 10 times 4 plus 30, which is going to be negative 10. And that will be in meters per second. Notice, by the way, that in terms of the units, dH is in meters and dt is in seconds. So you really do have meters per second here, even though maybe it's not really totally obvious that that's what's going on. But yeah, that is in fact what's going on. And if you write down the limit of delta H over delta T, well, delta H is in meters, delta T is in seconds, so it is in fact in meters over seconds. So the units do work out. And then the acceleration is the derivative of velocity, so it's just negative 10, and that's going to be in meters per second squared. Now, actually, one of the things that you may observe is that if your position function is following a quadratic, like it is in this example, then the acceleration is always going to be a constant. Why is that? Well, think about it. The second derivative of a quadratic is automatically constant, because every time I take a derivative of a polynomial, the degree goes down by 1. If I started with a degree 2 and I take a derivative, that gives me degree 1. Taking a second derivative brings me down to degree 0, which is a constant. So anything that is following a quadratic path, if their position function is quadratic in time, it's undergoing constant acceleration. And it turns out the reverse is true as well, although we will need to do a bit more work in order to prove that the reverse is true. But it turns out that, in fact, if something is undergoing a quadratic acceleration, if something is undergoing constant acceleration, its path is going to follow a quadratic function. This also leads to the fact that when we're talking about objects moving near the surface of the Earth, they follow parabolas. And it has to do with the fact that as long as you're not changing height too much, the gravity pulls you down at about the same rate, right? Gravity is actually proportional to the square of your distance from the center of Earth. However, as long as we're like just right near the surface, that square is not changing noticeably. As like if I throw a ball into the air, the force of gravity doesn't change noticeably between when it leaves my hand and when it's a couple dozen feet up in the air. So what ends up happening is it effectively follows a path given by constant acceleration, and thus it ends up following a parabolic flight path. This is one of the most commonly or early uses in physics because people were interested in things like, well, let's be honest, a lot of them were interested in military applications of things like, how do we aim our cannons at the, Napoleon wants to aim his cannons at the Prussians, or the Prussians want to aim back at Napoleon and things like that. So it was used for those kinds of things. But of course it has all kinds of other applications as well. And by the way, the force of gravity on Earth is about 9.81 meters per second squared. So that's at the surface of the Earth. That's about how fast hard gravity pulls us down. Also, I should notice that R squared business only applies if you are above the surface of the Earth. When you start going inside the surface of the Earth, things get way more complicated. So it's a difficult question in general to answer that. But as long as we're just near the surface of the Earth, it's actually very straightforward. Constant acceleration, and we end up with parabolic motion. Now, another example that we could ask would be, let's say that an object undergoing friction follows V of t is equal to, let's say, 3e to the minus 2t in meters per second. And we want to know what is the acceleration after 2 seconds. Well, the answer is a of t here is going to be given by negative 6 e to the minus 2t. Just take this derivative, relatively straightforward to do that, and then we can just plug in t equals 2. So a of 2 is negative 6, and this is in meters per second squared, negative 6 e to the minus 2 times 2. So this is going to be negative 6 e to the minus 4 meters per second squared. Whatever that comes out to be. Now, probably physicists and especially engineers, they may want to then give a decimal approximation to this. But, you know, we're doing math here. Let's leave everything exact. So that is our answer. Now, this is a fairly small number because e to the 4th is a fairly large number. So dividing by e to the 4th, this actually gives us a fairly low acceleration. But that's fine. I mean, that's just the answer that we get. Now, there's other sorts of questions that you can sort of ask as well that we will kind of address later. But for now, I'd like to point out that we can actually talk about questions like this in other sorts of circumstances as well. So it's not just about physics. We also get a lot of applications in other areas. An example of this is in economics, and in particular in manufacturing and things like this. We have something which is called the marginal cost. Do not ask me why they have to call it the marginal cost. I have no idea where they came up with this terminology. I don't do finance stuff really myself very much at all. So I don't know the history of where this was derived, but marginal cost. And to explain what marginal cost is, let's suppose that C of X is the cost of manufacturing. Okay, why can I not spell manufacturing? Manufacturing X units. Then the marginal cost is the cost of the X plus 1th unit. So the marginal cost at 100 means if I've already made 100 units, what is the cost for the 101st? Why would this be interesting? Well, the reason is because one of the reasons is something that we will see later, because it turns out that this plays a role in optimization types of questions. But what I want to say for now is this is not necessarily always going to be the same. And the reason is because of the following. Usually when we start manufacturing something, there's kind of a fixed cost per item. Like there's the material I put into the item, and I just have to buy that material. But there's also stuff like the machinery that I use to manufacture it, because I'm not just taking raw materials and magically transforming them. No, I have to have a machine or a laborer do work in order to get that item from the raw form into the finished product. Well, the thing is, the machinery that I buy, that costs the same amount of money, whether it sits there doing pretty much nothing or whether I use it 24/7. Except eventually it's going to get to the point where I'm starting to use it so much that it starts breaking down from overuse. So there needs to be like a balance, because if I buy an expensive machine and I only make one or two products, one or two units with it, then the cost of that machine is split among just one or two units that I've produced. If I use that machine to produce 1,000 units, well, now the cost of the machine is spread among 1,000 different units. So in general, the marginal cost is going to change depending upon what X is. And what we can then say is that this is approximately the derivative of the cost with respect to the number of units. So instead of actually calculating the marginal cost by, strictly speaking, what it is it would be the cost of the X plus 1th unit minus the cost of the X unit. But it's approximately the change in cost per change in X at whatever number of units we are at. So one of the things that we can do is we can say something like, maybe the cost of making X units of, I have no idea, some substance, some object, is given by C of X is equal to, and now I want to make sure that this sort of makes sense. So we're going to do, two x squared minus 1,000x plus 3,000. So why would this be the case? Well, essentially what's going to happen is, as I said, the more units I make, the more I am splitting the fixed costs of the machinery among the units. So in one sense, the more units I make, the cheaper it gets. But on the other hand, as I start to produce a really, really large number of units, then my costs for more laborers and more machines start adding up, and my cost for more space adds up. So maybe eventually it starts going back up again, but who knows? Anyway, we want to know, what is the approximate cost of the 501st unit? Well, if I take C prime of X, this is just going to be 4X minus 1,000. And what this means is that C prime at 500 is 4 times 500 minus 1,000. That comes out to be, why am I confused now? This is going to be 4 times 500 is 2,000 minus 1,000 is 1,000. Wow, okay, I just had trouble adding 2 and 1 or subtracting 2 and 1. So yeah, that's how this is going right now. Okay, hopefully you guys followed what was happening here. Now the point is, what this is saying is that if we've already made 500 units, it will cost me an additional $1,000 to make the 501st unit, or at least approximately $1,000, maybe not exactly. Now the thing is, of course, that whenever you're working with marginal costs, you're probably working with some degree of approximation to start with. Why? Because, let's be honest, you don't know for sure that this is the cost. Maybe we get lucky and our machine, the parts on the machine last an extra long time, like longer than they're supposed to. So maybe we don't have to replace the parts as soon as we thought we did, and the cost is lower than we expect. But maybe we get unlucky and one of the parts happens to break only halfway through its lifespan. Maybe it was supposed to last 6 months, it only lasts 3. So you're always kind of playing a bit of guesswork when you work with these kinds of things. That's why it's okay to just use approximations a lot in these kinds of applications. So there's another type of application that we can deal with. Let's think about some other sorts of applications that we can look at. So going back to a physics example, I want to look at the density of rods, one-dimensional rods, in other words. So this is another kind of example. So let's suppose I have a one-dimensional rod, and we'll say that this is at x equals 0, and x is going to be the length down here. Now, sometimes you have a rod that is made of a uniform material. In other words, it's the same exact material all the way along this thing. But sometimes that's not necessarily the case. Sometimes what we want to do is maybe we want a part of this to be made of a really strong material because it's going to be under a lot of stress. But as we go further out, maybe there's less and less stress. And so we can actually sort of get away with having less material further down. An example of this, and this is kind of an interesting one maybe, I find it interesting, maybe you won't, but let me tell you one situation where this comes up. Historically, I enjoy looking at things like the manufacture of historical swords. Well, historical swords, you can kind of think of the sword blade as a one-dimensional object. It's not really one-dimensional, but you can think about the length of it this way. Well, the density is not the same though, because when you are near the base that you're going to be holding in your hand, you need that part to be thicker to support the weight of the rest of the blade. But as you get down near the tip, you can have much less material out there. So the density as you move along is going to change like this. And in fact, archaeologists studying things like swords or other items that are maybe similar in shape or construction, they look at things like, oh, what is the density as we move along this thing? Now, supposing that I know mass of x, which is going to be the mass from 0 out to x. In other words, we start at one end of the rod being 0. M of x is how much mass is in this region. Okay, so that's what's going on here. Well, then the density is going to be, think about what is the density near some point. Well, the average density between x and x plus h is going to be m of x plus h minus m of x divided by x plus h minus x. The x's cancel. This is actually a difference quotient. And so in the limit, what we get is that the density at x, which is usually written as rho of x, this is actually equal to the derivative of the mass function with respect to x. So this symbol here that looks like a messy p is actually a Greek lowercase letter rho. R-H-O is the way that we write that in English when we're writing it out. And in physics, you often use the symbol rho to represent densities. So let's suppose for a moment that the density of a rod, or the mass function of a rod is given by m of x is equal to 3 over x plus 1 squared in kilograms. And we want to know what is the density. Well, the answer is I just have to take the derivative of this mass function. So if I want to take the derivative with respect to x, this is the derivative of, now I'm going to write this as 3 times x plus 1 to the minus 2. And this is going to become, using the generalized power rule, I'm sorry, I wrote this down in a way that really makes no sense. I was going to end up with a negative density. That's because my example was stupid. Let me fix my example for you momentarily. So it's what I want this to be is actually we want to have m of x is equal to 7 minus 3 over x plus 1 squared. There we go. I apologize. I was getting that mixed up in my head, and this is the example that I want to do. See, we're back to where I try to memorize the examples and do them sort of without referencing my notes so that things go more smoothly. They do go more smoothly because I don't have to keep pausing to look at my notes. But sometimes the whole writing things down from memory doesn't go so well. This is what we want to do. So then dm dx, this is the derivative of 7 minus 3 times x plus 1 to the minus 2. That is going to be positive 6 times x plus 1 to the minus 3, which is 6 over x plus 1 cubed. So that is our density function for this rod. Now, later on, we're going to see how you can actually do a lot of these things backwards too, which is what you want to do in many situations. Because in a lot of situations in physics, for example, you may not know the position. But what you do know is the acceleration, because you have control over the acceleration. Like maybe you're running a rocket, so you can decide what the acceleration is. And then you want to know what the position will be given a certain acceleration profile that you use on your rocket. Or maybe what you can control is the density, and you need to end up with a certain mass function as a result. So can we go backwards in the other way? The answer is going to be yes, but we're going to see that in a few weeks. The answer comes down to something called an antiderivative. But we need to, well, we could talk about those now, but to really talk about them precisely, we need a little bit or a few more results about derivatives in general. Okay, so that's sort of another example of these applications. Now, the truth of the matter is that there are all kinds of applications here. So here's one more where derivatives come up. Let's say that we are talking about an ecology problem. Or for that matter, maybe we are talking about a biology problem in a lab, growing a colony of mold or bacteria, or maybe you're out there and you're trying to cultivate viruses because you're trying to make a vaccine, let's say. I don't know. The point is, we're talking about something with a population. Well, then the rate of change of population P is going to be P of T2 minus P of T1 divided by T2 minus T1. So the instantaneous rate of change is going to be the limit as T2 approaches T1. The instantaneous rate of change, therefore, is just going to be P prime of T. In other words, it's the derivative of the population function. So this means derivatives can show up in biology. Now, in some sense, this is kind of approximate again. And the reason is because in biology, you can usually only have a discrete natural number or whole number of individuals, I should say, because you could have 0 individuals, you could have 50 individuals, but you can't have something like pi individuals. However, when we're talking about functions that model these things, we can often at least approximately talk about the instantaneous rate of change. So yeah, it's true that the instantaneous rate of change, actually the way that the population goes is in steps. but it's close enough to one of these differentiable functions that this sort of thing is useful for it. Another case where this comes up is in medicine. Like, let's say that we have the concentration of some sort of medication in the blood is given by C of t. Well, then the rate of change of the concentration will be C prime of t. So once again, we see derivatives come up. Now, here's the secret. Like, what is uniting all of these different examples? What unites the examples is we are talking about rates of change. And everything that can be expressed in terms of rates of change is related to derivatives. At least if we can cast it into a form where we can talk about, functions and things like that. So if we can model some quantity with a function, then we can say, if we want to talk about instantaneous rates of change, we can look at derivatives. Now, again, you got to be a little bit careful when you're talking about things like populations, where actually the variable only takes on whole number values. So it's not as if, like, when we say that the population's rate of growth is 230 individuals a year, we don't mean that literally they smoothly drop out over that time. We mean there's sort of going to be 230 individuals over that year. And we're approximating this using the derivative because, again, it is a discrete variable rather than a continuous variable. But because it's so easy to take derivatives compared to just finding differences and things like that, we often say, look, we can approximate this with a smooth variable. It may be a discrete variable, but let's just approximate it with a smooth variable, a continuous variable. That way we can use the techniques from derivatives, and that'll make our calculations really, really easy. And they'll be close enough for whatever purposes we happen to have. Now, one of the observations that I want to make here is that there is a particular type of function that has a really nice property. So notice that if I have ae to the kt, if I take the derivative of this, this ends up being k times ae to the kt. In other words, why did I put an equal sign there? The derivative of this, if I think of this as f of t, the derivative with respect to t of f of t is actually equal to k times f of t, because this is, once again, just f of t there. A lot of things in the real world turn out to be modeled by something that obeys this kind of a relationship. So what we're going to do next time is we're going to come back to looking at applications into the real world, but we're going to be focusing in on stuff that gets modeled like this. Well, it turns out the answer is always going to be, it's modeled by an exponential function. So in the meantime, you can probably spend some time think about your own favorite topics of study, and think about, like, where could you measure rates of change there, and how derivatives might be useful in those contexts. But in the meantime, we're going to leave this until next week to really delve into this further.